Good afternoon, everyone. First of all, I would like to thank you for giving me this opportunity to speak in front of you. So my name is Tejas, and I'm from DeltaXML. So today, along with my colleague Nigel, we are going to talk about different varieties of XML merge and how they differ with respect to each other. So let's just see what we are going to cover in this session first. So first, I'll give you a brief background about what we are trying to merge and what is this merge is not about. Then we will talk about concurrent merge, sequential merge, what is the difference between those two. These terms, concurrent and sequential, these are our terms. We wanted something meaningful so that it will explain the process as well, and we can name them, we can name our Java classes along with them. After that, my colleague Nigel will talk about merge processing, a different kind of merge that is Graft, and then we will finish off with some questions and demo. So what are we merging? We are merging trees. Those could be XML and JSON. We are merging documents and data. We are merging XML standards like docbook, data. So what is this merge which we are proposing is not about. It is not a two-way merge, which is essentially a comparison between two documents where we combine two documents into one. This is not a line-based merge where we lose the original structure of the XML document. So what is it? First, we will talk about the concurrent merge. Inspiration for the concurrent merge for us came as a software developers. So those of you who have followed the different version control system like RCS, CVS, SVN, and now Git and Mercurial, will know that everyone was delighted when SVS introduced merging of branches, which allowed us to work parallelly. So we thought that why can't we do that with the technical documentation? So we spoke with our customers, and then we came across the test cases like if there are 5 authors and they are changing the same technical documentation at the same time, and at the end of that we want to visualize all of them together into one. So can we do that? With the Git and Mercurial, you can get those into a final one document, but we don't have the full context while merging because it's a 3-way merge. So can we do more? Is the 3-way merge enough? So to do more, we need an n-way merge. So concurrent merge starts with an ancestor where each version is a derivative of that ancestor. Then all of them together are merged together into one single document, which is an intermediate representation into an XML file of all the versions and the changes made by them. That intermediate representation can be then processed further to visualize or whatever we want to do. The second type of merge is sequential merge. So for sequential merge, our inspiration mostly came from the customer use cases and the test cases like traveling draft, where the legal documents are passed between two different parties, one after the another, which creates number of versions at the end of the chain. So what they want to know now is what are the changes by each and every person, and specifically what are the deletes rather than the additions and the modification. So can we merge all those versions into one document together? So sequential merge does that. So just like concurrent merge, it takes multiple number of XML documents, minimum 3, maximum could be anything. It merges all of them together into one document. There is a clearly defined order of edits over there, so we can understand the result by looking at it. Sequential merge mostly applies to the document-centric data, where I can give you 1 or 2 examples of it, where in Confluence or in WordPress, if you look at the document, if you look at the version history of it, it allows you to see the number of versions of it. And at the end of the merge results will allow you to see the contribution from each and every author. But someone could argue that why do we need sequential merge? That I can keep everything in one directory and then compare two documents together to see what happened between them. but it doesn't give us the full context of the changes. That's why we need a sequential merge. So what is the difference between sequential and concurrent merge? First difference is the inputs itself, how the process of updates of inputs happens. The second one, how those inputs are aligned, then how those inputs after alignment are processed internally, and what is the change representation of each and every input at the end of the merge. We will look at each of them briefly over here, but they are explained in detail with examples in the paper. So first of all, alignment. So as we discussed in concurrent merge, every version is derived from common ancestor. So every version gets aligned with the common ancestor. Contrary to that, in sequential merge, every version gets aligned with the previous version because it's an update to it. But while aligning so, what are the different criteria we use to align the elements? So there are different criteria like element name, their namespaces, then similarity of the text content, keys, and the order of elements. So while aligning, first merge process tries to identify the optimum alignment of corresponding elements by calculating the longest common subsequence. So if you are merging two elements, then the elements which are exactly same gets the precedence over the elements which are same only with respect to their names. However, if the text is slightly different, then depending on the similarity of the text, those elements get aligned. Merge also gives a user control over the alignment process where every element can have its own keys and those keys can be used as an alignment. So these keys can be used, the attributes can be used as keys. While doing so, in some documents, the order of the element is very important. And some document, order of the element is not that important. For example, if we have a document where if we change the order of the element, then it totally changes the meaning of the document. Whereas in the documents where we have databases, order of the element is not that important. So do we want to maintain the order of the original document into the merge result or not? Depending on that, we can decide whether do we want to do merge with ordered or the orderless comparison. So if you look at this diagram now, this is the overall workflow of the merge where you can see there is an ancestor and version V1, V2 and V3, and each of the versions is first compared with the ancestor, which produces a comparison result. Each of these comparison results are then stitched together to get a final merge result. Similarly, in sequential merge, because there is no concept of ancestor, every version gets compared with the previous version. Just like over here that V2 is compared with V1, V3 is compared with V2, and V4 is compared with V3. And the comparison results of both of them are stitched together to get the final result. If you see both of them, in both of them, the comparisons happening are exactly, the number of comparisons are exactly same. So how they differ are in terms of inputs, in terms of alignments, and how they are represented. So this is the simple example of the inputs and its change representation. So if on the left side, you can see there are three documents, document A, document B, and document C. These three documents can be merged concurrently or sequentially as well. We need to decide whether these documents are updated concurrently or sequentially. So if you look at the document A, which has first element P1 and then P2, if we consider that document B and document C are edited concurrently from document A, then we can see that document B doesn't have a P1 element, so it's a delete. Whereas there is a document P1 in document C, which aligns with the document P1, and document B also adds a P3 element, whereas document C also has a P3 element. So if we look at the concurrent result now, because it's edited concurrently, we can say that the first P1 in document A and the P1 in the document C, they align with respect to each other, and that's why we see the differences between those two. However, if we do this sequentially, document A also has P1, document B deletes P1, document C adds P1 again. But with respect to sequential, if something gets deleted, then it never comes back to life again. So if something is added by previous version at the same position, then we can say that that's a completely different paragraph or the element. That's why when you're doing the sequential merge, there are two P1 elements, one which is added, one which was there in C, A, and one then deleted by B, and then which was added later on by C. Now if you see the paragraph P3 over here, added by P1, sorry, document B, then in concurrent merge result, it shows that it is only added by B and it only exists in B. But if you are doing it sequentially, if something gets added, then it gets carried forward to the next version until it's deleted. So that's why you can see that even though B adds it, it exists in C as well. So if you are confused with the deltas over here, my colleague Nigel will explain more about this delta and how we analyze those deltas and how later merge rule processing can be applied to extract whatever we want to extract out of it. So Nigel, please.
Thank you, Tejas.
Thank you.
Thanks. So Tejas has mentioned deltas. I will try and quickly explain how we use them to process the merge. So deltas represent the inputs to the merge process, and so they're given identifiers. In this case, from the following example, A corresponds to the ancestor, and we have V1, V2, V3 coming in. From those, we separate the deltas with equals and not equals, and those are both used as separators, but they also tell us about subtree equality at that point, so that we can make some calculations from. The other thing to say is that not equal has higher precedence to equals, and then you can. Okay. So not equal has higher precedence to equal, and therefore you can group the create subgroups from them. So you can also do calculations about concepts such as deletion and addition based on them. So element 1, you'll see wasn't present in the ancestor, and therefore we can deduce that it has been added. So the parent has A in its delta, but element 1 doesn't. So in order to do these calculations of addition and deletion, you need to look at an element and its parent to derive some of these rules. So looking at the element 2, we can see that the ancestor is present both in element 2 and the parent, but there are fewer versions in element 2, and that tells us there's a deletion. You can do set difference, and you can calculate who did the deletion. So that gives you a feel of the delta calculation. This fits in with the idea of concurrent merge. We have the ancestor, that gives us the temporal frame of reference. We can then define addition and deletion, and we can define conflict. So element 1, we can see we've got a V1 not equal to V2. So we can say there's some change under those subtrees, so that is a conflicting add. So that forms the beginning of how we can process the merge result. And we've looked back to things like Git and Mercurial and thought about how they do it. And if you consider those systems, you typically do a merge in a software version control system. And what you will see is conflicts. What tends to happen before you see the conflicts is non-conflicting additions and deletions are automatically processed. But we have asked ourselves, and customers have debated with us as well, why things have to work that way. It tends to be a symmetrical process, and we've considered that some asymmetric forms of merging might be more useful. So some of the questions posed are, when I'm doing a merge, I've typically worked on a given branch. I'm merging someone else's branch, and I know more about what I've done than the other branch. I might want to see the conflicts, but also the changes on that other branch. And another use case is deletion. So if you think about API compatibility, you prefer not to delete an existing method because that breaks your API compatibility. Adding methods is okay. So in some cases, people care more about deletion than they do addition, another kind of form of asymmetry. And so there are different kind of processing models you can apply. Another one we've met is we don't want to deal with conflict. We want an automatic system, and you can use an ordered priority list of the versions and use that to, for example, resolve conflicts. These things can be applied globally, or you might decide that you want to use the power of something like XPath or JSON pointer to apply different types of rule to different elements or different subtrees. So these are how we do rule processing. You could do a similar kind of thing in a merge user interface. A graphical tool could make similar kinds of processing choices and decisions. So quickly moving on to some of the unique features you get from a tree merge. One of them is the concept of nested change. So with 3 or more inputs and a tree-structured representation, changes can nest. So in the example on the right-hand side, we created a proof of concept demonstration of this in Oxygen a few years ago. And one of the things we're trying to show, you might not be able to read what's on the slide, but the important thing is the red represents something like a paragraph being deleted, and inside that, an addition has occurred, which is represented in the green. So those kind of nested changes are sometimes difficult to represent in an interface which deals with a kind of sequential list of change, which is what a line-based algorithm would do. And that kind of makes us think a little bit more about different kinds of user interface for handling nested change. And we'd argue that nested change is better handled with an interface that allows you to manipulate that in a kind of tree structure. Now, we realize that we are kind of introducing something that is against convention here. So we also think that there are ways of making compatibility. So 3 to 2 is a process of turning something like that into something which fits existing user interface models, such as the accept-reject mechanism you find in track changes. So there are ways of turning something that's nested into something that's simple and linear, makes it easier to process and use with existing user interfaces. So we've only done that for three-way, to a 3 to 2-way process. It reduces some of the granularity of the information, may introduce some duplication. So Tejas mentioned the use case of N-way merge. So a number of editors want to work concurrently on a document, perhaps 4 or 5 of them, and at the end of the process, you want to bring those changes back together to produce the next version. So people have asked us, if I have a 3-way merge, can I not just repeatedly apply that and achieve it? And on the left-hand side of the slide, I've kind of mocked this up in SourceTree, giving you a screenshot of the repeated application of a 3-way merge process to merge multiple branches together. One of the issues that this presents is that when you are at this point, you might not know what's coming up, or when you've got to the final point, you might say, I would have actually preferred a version I saw earlier on. And so one of the things that we did in our proof of concept was introduce this little button you click on, and it can show you N-way conflict. And so you can be more informed about the different branch alternatives in a single operation rather than having to make successive merges. Finally, a little bit of discussion on Graft. So Graft is a little bit like Merge, and so we're trying to illustrate it with a picture here. So you might have one branch and you might say, I want to pick a number of changes between A and C, apply them to a target branch T1 to create a new version on that branch, let's call it T2. In this scenario, it's harder to define conflict. You might be able to say that between A and C you have the concept of addition and deletion, but because these two branches effectively go off into infinity, they're parallel, you might not meet at a common ancestor. And so one of the things we had lots of philosophical discussions about is, can we define conflict in this case, or should there be more forms of automatic processing? And so I've indicated a screenshot on the bottom from our new JSON graph system. And we have 3 different modes of applying those changes that are based on the kind of rule processing we've already mentioned. But none of them present the user with a conflict. So we've taken a slightly different view of Graft as a distinct concept. It's using the same ancestor, so there's kind of a fake ancestor, which is A, and then we process that to create, so we're applying the same kind of workflow that Tejas showed for the concurrent merge slide, but we're doing slightly different rule processing, which is conflict-less. So we try to create a sentence to say what a merge is, and we think merge means lots of different things to lots of people. It's about the alignment approach, whether you take the common ancestor or whether you take successive versions. We create a merge tree using that alignment. Some people consider it about the algorithms you apply. Do you talk about conflicts? Do you talk about additions, deletions? To other people, it might mean more of a user interface. So they think of conflict resolving systems where you can move things between versions to do your conflict resolution. So we feel that all sequential, concurrent, and graft are different concepts. We're still working on clarifying the precise details of how the processing of the rules will work. The one thing I think we've learned is that software version control systems have done things in a very similar way since the days of CVS. And where merge was introduced as a three-way process, we think there's more possibilities if you open your mind to what the requirements are and think of different use cases and try and put the software version control systems to the back of your mind. Okay, so thank you. We have a few minutes for a demo or questions. How are we doing for time? We didn't start the
You have to share microphone because there is some technical issue with other one. So, questions? Oh, come on.
Should we show a
See
demo?
a few presentations about diffing, and there will be some more. Mohammed.
Okay.
Over there.
Yeah, I'm going to ask a question about, it's indirect. It's, I once upon a time was a co-chair of a XML change tracking community working group, and it doesn't much, due to my fault, mostly, make most contribution, but is there still a plan from you guys to contribute this work as a standard or more as an implementation and proof of concept so far?
The change tracking working group seems to have stalled from our perspective. We have created a proposal for how to track changes and use that information. We think they are not the merging and change tracking are not the same technologies. Change tracking records what the user does. It can generally do a better job if it's enabled. So we'd like to see progress in that area, but it needs implementers to implement them in editing systems, I believe, to make progress. We are not in that position to implement that ourselves.
But for merging, do you plan to contribute it to as a standard?
It's a possibility. We're trying to explain some of our thoughts on different merge scenarios here. As Tejas mentioned, we had a problem when we tried to say, what do we call our classes in our Java API? And we heard terms such as traveling draft, and we've come up with sequential merge, concurrent merge. We want to talk about trying to pose more thinking about n-way merge.
Thank you.
So, more questions? So if not, thank you again.
Thank you.
Thank you.
Thank you. Thank you.